Hi everyone, thanks for inviting me. I'm happy to be here. Today I'll show you how malware can disable Microsoft Defender by abusing system mechanisms and how to avoid this kind of attacks. I think that this topic is of crucial importance for all experts dealing with endpoint security and antiviruses experts. This work was done in collaboration with one of my students from National Research Nuclear University. Dennis investigated attacks on Microsoft Defender in his bachelor thesis under my supervision. I'm eager. I've been exploring OS security for more than 10 years. I've been curious about discovering new attacks on Windows kernel and finding the ways to prevent them. Today, I'll highlight that one of the recent malware trends is to disable endpoint security solutions. I'll show you the analysis of attacks on Microsoft Defender. We'll address the kernel attacks that can tamper with security solutions, and I'll give you a new attack that can blind vast majority of antiviruses, including Microsoft Defender. Finally, I'll present you my MemoryRanger, the tool I designed and customized to protect Microsoft Defender. After gaining an initial access, cybercriminals always want to steal users' data and perform lateral movement, to install a backdoor and take the control for a long time, to encrypt users' files and demand a ransom payment. To achieve these goals, attackers can download and install the malware. To avoid signature-based detection on firewall stage, attackers can use passwords-protected archives. Attackers can extract the packed malware sample and launch malware to reach all the desired goals. But antiviruses and security solutions can detect all these malware samples and remove them easily. Attackers are always up to disable or blind security solutions. Such attacks result in disabling security solutions, and after that, the malware can be installed without triggering any security reaction because the security solutions are disabled. Criminals are always looking for the ways to attack antiviruses using both user mode techniques and kernel mode techniques. This is a serious problem for security solutions and even for Microsoft Defender. You know that Microsoft Defender is installed as a primary antivirus on more than half a billion devices. The patent director at Microsoft underlined that Microsoft Defender is facing a huge number of various attacks. Many security experts share their ideas about how to disable and bypass the Microsoft Defender. They discussed code injection, packing malware to bypass signature detection, manipulation with exclusion path of Microsoft Defender, abusing trusted installer to stop the Windows Defender service. Hackers leverage these techniques in their malware. Here are the malware examples which are able to bypass Microsoft Defender. Ragnarok ransomware that modifies registry, Z-Loader banking Trojan that uses PowerShell scripting, Kraken botnet that adds itself in the exclusion path. Various modern malware programs are attempting to disable Microsoft Defender. Global cybersecurity community widely discuss the attacks on Microsoft Defender. Here are some recent academic papers, blogs, and research talks that show how to bypass Microsoft Defender. Let me show you the current attack vectors on Microsoft Defender. All attacks can be divided into two groups: user mode and kernel mode attacks. User mode attacks target mostly user space components, while kernel mode attacks can tamper with kernel mode parts. Regarding user mode vectors, attackers can change the configurations of Microsoft Defender and even terminate its process. Attackers can implant the code into the whitelisted processes, for example, to access Internet without any obstacles. Attackers can confuse Microsoft Defender by modifying the file's content on the disk after the image has been mapped. Attackers can use various techniques to bypass file scanning engine of Microsoft Defender, such as packing and obfuscation. Attackers can manipulate with anti-symbolic links, which pushes Microsoft Defender to follow the wrong path. Attackers can bypass kernel callbacks to spoof the process name so that Microsoft Defender will receive a fake app name. Attackers can isolate Microsoft Defender so that it cannot access any file or process. This attack was published just a couple months ago, but this attack can be blocked by Windows feature named Trust Label. My student Dennis has independently discovered the kernel attack that produced the same result and cannot be blocked by trust labels. Okay, one more kernel attack can blind Microsoft Defender by attacking Event Tracing for Windows (ETW). Attackers can disable Protection Process Light (PPL) to terminate Microsoft Defender. Attackers can blind security solutions by removing kernel callbacks. Attackers can terminate the Microsoft Defender process by calling the termination routine from a kernel driver. To show the details of the discovered attack, let me highlight some recent trends in driver-based attacks. Using the first technique, hackers can install any signed vulnerable driver and exploit its bugs to access kernel. Researchers from Rapid7 showed about 30 malware examples that exploit various legitimate drivers. Attackers can also use leaked digital certificates to sign their malware drivers. Let's look at some cases. The notorious hackers group targeted NVIDIA to steal confidential information. The data leak has been confirmed, and the stolen digital certificates have already been used to sign malware. Hackers can easily buy leaked certificates using dark web market. Now I want to raise concern about Windows hardware certification program. You know that developers can submit their drivers to the Windows Hardware Quality Labs that checks whether this driver is compatible. If the driver passes the check, it will be signed using a special digital signature. But Microsoft has accidentally signed malware drivers, such as NetFilter driver and 5Cs driver. Both of them are malware. Another big trend is malware implants working on firmware level. Such bugs in UEFI firmware can impact millions of devices. We can conclude that driver-based attacks are still very important. Let me introduce Microsoft Defender. Microsoft Defender has about 20 years old history, releasing as a free anti-spyware program, and nowadays it is a leader in the endpoint protection platforms. Let me uncover Microsoft Defender components. Microsoft Defender includes user mode applications such as processes and services and kernel mode drivers. All in all, there are about 10 apps and 6 drivers. In this research, we analyze Microsoft Malware Protection Engine process, MSMP Eng, and Microsoft Defender File Filter driver. The process is just a normal Windows app that can detect the malware on the disk and in the memory. One of its DLL modules, named mpengine.dll, implements the signature-based detection. It is the brain of antivirus engine that decides whether the input is malicious or not. An idea of the attack is to block the brain from receiving input data. I'll show you how Windows built-in mechanism can be used to disable Microsoft Defender. Let's look at the Mandatory Integrity Control, MIC. Each time any app, for example Microsoft Defender, tries to access the object, for example open a file, the Security Reference Monitor checks whether this access is allowed. It was originally based on Discretionary Access Control, DAC. Mandatory Integrity Control, MIC, has been added in addition to DAC. MIC was designed to isolate untrusted apps from the rest of the OS. Now we have two different access checks. DAC checks privileges using access token and security descriptor, while MIC reads and compares integrity level from access token and integrity level from object descriptor. Windows first checks an access request against MIC, and if it passes, then it checks DAC. To allow access, it has passed both checks. But if MIC check didn't pass, the access will be blocked. Attackers can patch integrity level for the Defender so that any Defender's access attempt will be blocked. To demonstrate this attack, let me first focus on integrity levels. Windows supports several integrity levels to limit access to the resource. Untrusted and low integrity levels are usually used by browsers to isolate web threads from the OS. Most apps that we use are running with medium integrity level, such as Explorer, Notepad, Office, and etc. High integrity level is assigned with apps launched by User Account Control UAC. System integrity level is used by system-level apps such as Microsoft Defender to protect them from other apps. Here is an example of integrity levels for the running processes and files on the disk. MIC implements the Bell-LaPadula access control model, you know it. For example, an app tries to get write access to the file. According to the Bell-LaPadula model, access check compares integrity levels of app and a file. The access will be granted if the app's integrity level is equal to or higher than the file's integrity level. Therefore, apps with low integrity levels cannot override the most OS objects. Let me show you how integrity levels are implemented in Windows. For each app, Windows allocates a separate data structure in kernel memory named eProcess. This structure contains process name, process ID, and other process attributes. This structure points to the token structure that includes all information about the process privileges. The set of process privileges is stored using security identifiers, SIDs. To support MIC, the following two new fields have been added: integrity level index and the corresponding seed and attribute structure. Integrity level index is just an index into the array pointed by the user and groups. This entry points to one of the integrity level seed. For example, an example of SIDs are here. Let me show you how Windows gets these integrity levels. An app can get or read the integrity level of the target app by calling getTokenInformation with the parameter. The control goes to the ntQueryInformation function from ntdll and then to the kernel. We have a list of function calls, and finally the control goes to the function sep locate token integrity. Let's see inside it. The function receives the pointer to the token structure and it returns the pointer to the seed and attributes. The function reads the integrity level value. If it is -1, the function returns 0, or else the function returns the address of the structure that points to the integrity level SID. The return value is used by the function sep copy token integrity. Let's see how. The function receives the pointer to the token structure and it fills the output pointer. The function first calls sep locate integrity to get pointer to the seed and attribute structure. If return value is non-zero, the corresponding data are copied to the output. Or else, for the zero value, the untrusted SID and its attributes are copied to the output. It means that by setting -1 to the integrity level index, attackers can mark the target process as untrusted. Let's see how it can happen. At first, attackers can load kernel driver to override the integrity level index, and after that they can extract and launch a malware sample. We will see if Defender will be able to detect malware files and malware process. A few words about the infection part. The Mimikatz app will be used as a malware. We initially zipped Mimikatz with password. Here is the batch script that extracts the Mimikatz from the archive file and launch it. Let's see how it can happen. Let's check the Windows version. We have the newest one. Checking the integrity level for Microsoft Defender. It is system level. Let's run Process Monitor to track files activity. Apply a filter to monitor only malware activity. Run cmd with admin privilege. Run a script that extracts the archive and launches Mimikatz. Attackers failed to run Mimikatz. Microsoft Defender detects a malware sample. And also, Microsoft Defender removes a malware sample. Let's double check that the file is removed. Yes, it is. Let's see the logged file system events. Move to the end. Microsoft Defender deletes Mimikatz file by changing the file information. After closing the file handles, the file will be removed. We've just proved that Microsoft Defender is active. We're launching the DBG view to see the kernel output. The attacker is launching the app which loads the driver. The attacker patches integrity level index. We can see that integrity level index has been modified. Let's extract the archive and run Mimikatz again, we can see that now the situation is different. Microsoft Defender can still detect malware, but it can't remove the file. Let's run Mimikatz. We can see that OS cannot run Mimikatz. Let's see the logged file system events. We move to the end and see that OS returns 906 status. Let's clear the log and relaunch Mimikatz. CMD fails to run Mimikatz and the OS returns 906 status. Each time attackers run Mimikatz, the OS returns 906 status. Let me conclude. Patching integrity level index helps to prevent removing Mimikatz file, but it is not enough to allow launching Mimikatz process. Microsoft Defender fails to remove the file, but it is still able to block the running processes. We've just seen some Microsoft Defender internals. It uses pending deletion state to remove the malware file. Also, we've been seeing a new status that blocks creating a malware process. Let me show you the driver that returns this status. My research has revealed that this status is returned by Microsoft Defender file filter driver. This driver registers a mini filter to monitor file operations using pre- and post-processing callbacks. I have discovered that post-create callback function returns this status for the malware apps. It means that Microsoft Defender can still detect malware in apps memory. But how? We know that malware detection engine is located in the Microsoft Defender process. Each time the Defender process gains the access to the running process, Windows checks where the privileges are enough using access token and security descriptor. However, Defender process has debug privilege. As we know, for processes with debug privileges, Security Reference Monitor always allows full access without any checks. Attackers can revoke debug privilege from Microsoft Defender to restrict this access. The mentioned privilege is stored in token structure in memory, and it can be patched by attackers. Let's see how it can happen. At first, attackers load the kernel driver to perform both actions, to override the integrity level index and revoke process privilege. After that, they can extract and launch a malware sample. Let's see whether these manipulations will be enough to disable Microsoft Defender. Let's check the Windows version. We have the newest one. Checking the integrity level for Microsoft Defender, it is system level. Let's run Process Monitor to track files activity. Apply a filter to monitor only malware activity. Run CMD with admin privilege. Run a script that extracts the archive and launches Mimikatz. Attackers failed to run Mimikatz. Microsoft Defender detects a malware sample. And also, Microsoft Defender removes the malware file. Let's double check that the file is removed. Yes, it is. Let's see the logged file system events. Move to the end. Microsoft Defender deletes Mimikatz file. We've just proved that Microsoft Defender is active. We're launching dbgview to see the kernel output. The attacker is launching the app which loads a driver. The attacker patches integrity level index and revokes a process privilege. We can see that integrity level index has been modified. Here are the privileges before and after patching. The debug privilege has been cleared. Checking the integrity level for Microsoft Defender, it is untrusted now. Checking the privileges, the debug privilege has been disabled. Let's extract the archive and run Mimikatz again. Mimikatz has been started. Let's use these commands to extract passwords hashes. The hashes have been dumped. Let's see the logged file system events. Move to the end. We can see that now Mimikatz has been loaded. Let's check Windows security settings. We open Virus and Threat Protection. Allowed threat. There are no allowed threats. Let's check the updates. Microsoft cannot be updated. Let's wait for PatchGuard reaction, which was designed to prevent attacks on Windows kernel. Ten hours have passed, nothing has happened. The OS is in danger. We can see that Microsoft Defender has been completely disabled without triggering any PatchGuard reaction. This attack results in sandboxing or isolating Microsoft Defender from the rest of the OS. The key point is that we don't terminate Microsoft Defender. It is still running, but it cannot detect any malware on the disk and in the memory. Microsoft Defender has been disabled. What about other popular antiviruses? Here are the results of checking the given attack against top Windows antiviruses. We can see that vast majority of antiviruses has been successfully disabled. This attack is very dangerous. Let me show you how this attack can be blocked. In Windows kernel, drivers share the same memory space with the OS kernel. There is no built-in mechanism to restrict illegal access attempts to the kernel memory. I designed MemoryRanger to solve this problem by allocating a separate kernel enclave for each newly loaded driver. As a result, drivers are running inside separate enclaves with different memory access permissions. This scheme helps to block illegal access attempts with affordable performance degradation. Originally, I designed MemoryRanger as a tool, as a framework to monitor access to the kernel data. Now, MemoryRanger can hook kernel functions. It can locate very sensitive data in kernel. It can be easily customized. Let's have a look. Here are the examples of MemoryRanger customizations that block various new attacks on Windows kernel. In this research, MemoryRanger has been customized in the following way. Without MemoryRanger, attacker's driver can get access to the token structure. MemoryRanger traps loading of attacker's driver and moves it to the separate allocated enclave. In this enclave, the token structure cannot be accessed. Let's see how it can happen. Let's check the Windows version. We have the newest one. We're launching DBG View to see the kernel output. Run MemoryRanger to protect kernel memory. We can see that MemoryRanger is ready to protect token memory. Attackers are launching the app which loads the driver. And look, MemoryRanger has moved the attacker's driver to the separate enclave. Attackers are patching integrity level index. And look, MemoryRanger has blocked this illegal access so that attacker's driver reads fake null index. Attackers are revoking process privilege. And look, MemoryRanger has blocked this illegal access as well, so that attacker's driver reads fake null token. Run cmd with admin privilege. Run a script that extracts the archive and launches Mimikatz. Attackers failed to run Mimikatz. Microsoft Defender detects a malware sample. And also, Microsoft Defender removes the malware file. Let's double check that the file is removed. Yes, it is. Checking the integrity level for Microsoft Defender. It is still system level. Checking the privileges. The debug privilege is still enabled. Thanks to the MemoryRanger, the Windows OS and Microsoft Defender are protected. Let's discuss very briefly what we've seen. Without MemoryRanger, attackers disable Microsoft Defender and install malware without any problem. Microsoft Defender fails to remove the malware. But with MemoryRanger, the situation is different. MemoryRanger allocates the default enclave for the OS kernel and all previously loaded drivers. MemoryRanger traps the loading of attacker's driver and allocates a separate memory enclave for this driver. In this enclave, MemoryRanger restricts any access attempt to the token structure of Microsoft Defender. As a result, attackers failed to disable Microsoft Defender. This is the way how MemoryRanger protects Microsoft Defender. Let me recap very briefly on what we have discussed so far. First of all, driver-based attacks are crucial. Intruders are plotting to bypass endpoint security solutions, and their target number one is Microsoft Defender. Attackers can apply MIC and token privilege against Microsoft Defender to isolate it. This is very serious attack because it blinds vast majority of antiviruses without triggering any page guard reaction. I have presented my MemoryRanger that customized version can prevent this kind of attacks. Thank you.